Hello, Anandi Ghosh. Hello. Hello, Anandi Ghosh. Am I audible? Yes, sir. Okay, thanks. And are you able to see my screen? Yes. So, are you able to see my handwriting? Yes. Okay, thanks. So, let's wait for a few minutes and join. Let them join. Let join other people. Then we will start. Record view हो रहा है, इसको कर सकते हैं कम से कम। So okay, welcome Anandi. Let them join let join other people. Then so I will start now. So I will solve question and answer after I have prepared some introduction for this course. Then we will going to there is one person. Okay. Then we will going to solve this question answer assignment courses. So I am Bhupendra Singh, pursuing PhD from the IIT Kanpur in the Department of Chemistry under the guidance of Professor Pratik Sen. So this is my first NPTEL course. Probably you will see some mistakes, so ignore that and try to learn. Okay, let's start then. I think he left, that fellow. Okay, no problem. So this is group theory. So basically, what in this group theory course we will going to see uh, lot of content like access or these symmetry elements, then operations. But I'll not go as you are seeing in the NPTEL course. I have prepared my content and I will going to address that only. But I am pretty sure, I assure you that you will going to learn something from it. So this group theory is basically what it is. It is the see Okay, so it is the mathematical study of basically of symmetry. Okay, so after doing confirmation and orientation of any symmetry, any molecule or any object, we will going to get the equivalent orientation and identical orientation. So basically conformation or orientation of any object or molecule will, after the operation, we will lead to the equivalent orientation of that particular object or molecule and the identical orientation. So what are the difference between these two? Equivalent and identical. So let's take one example of water molecule. We can rewrite as here. Let's say H1 and 2. They are identical. They cannot be distinguished. But for our purpose of studying this symmetry, this course, I am indicating both the hydrogen molecule as 1 and 2. They are actually no different, but so by, let's say if I reorient this water molecule 180 degree, how it will look like? Of course, I have to give axis of operation, that where I am going to put the axis of the molecule from where I am going to rotate this molecule. So let's say this is the axis of rotation. After rotating it at an angle of theta of 180 degree, you will see a structure like this. Let's say, okay. After that, if you again do the same operation, rotating it at 180 degree, what you will get? You will get something like this. So as I have already told you that what are the differences between these two equivalent and identical structure. See, if you look closely, this H1, H2, H2, H1, actually they are no different, but for studying this course I have indicated like that, H1, H2. So if you look closely, these two molecules are equivalent but not identical. If you compare first one and third one, these molecules are equivalent, identical. So this is the basic difference. So I would say 1 and 2 are equivalent orientations, and second, third and first, the identical. Now, what are the tools for mathematical? Okay, there is one person. Harini. So, tools for mathematical study of symmetry. First one is symmetry element. And upon using the symmetry elements, we do the symmetry operations. So, let's say this is your, in this one, this is vertical, this is horizontal. So, if someone really wants to rotate this, we have to, from vertical to horizontal, we have to rotate it by 90 degree. 90-degree rotation should be there. And if someone wants to, let's say I'm putting 1 here and 2 here. Let's say, for example, let's say it is vertical to vertical, but 1 to 2. So it is like top to bottom. So what should be the operation here? We should rotate it like rotated by 180 degree. Rotation should be there. Then we will reach to this orientation from here to here. And from here to here, we have to rotate by 90 degree. Now, coming, as I have already introduced, these are the symmetry elements and symmetry operation tool for studying the symmetry. So let's start from the symmetry elements first. So what are the symmetry elements? First, is axis of symmetry, AOS. I am just writing the short form abbreviation. Axis of symmetry. Second one is plane of symmetry. This is coming again and again. This is third is a point, inversion point or point you have already seen. So these are the elements. Okay, these are the any geometric entity, let's say what I have introduced: axis, plane, or point. Last one. over which we apply symmetry operations. These are the elements over which we apply the symmetry operations are called symmetry elements. Okay. So what are the okay next one fourth one is I have forgotten. I think it is this improper access of symmetry. Improper access of symmetry. IAOS. So now coming to the symmetry element, this symmetry operations. So this is the basically the introduction. Then we will do the question answer. Okay, first one is rotation, which I have already introduced you here. Something rotation, this 90-degree, 180-degree something. So this is the rotation. These are the operations. Second one is reflection. Third one is inversion. The rotation, how we can rotate a molecule or any object? It should be about over a axis. Next one, reflection. We should have to have the plane, just like we have mirror. Next, for inversion, everything is like inverted, so you should have point. So these are which I have already introduced. These in bracket whatever I have written, these are the symmetry elements over which we do the symmetry operations. These are the symmetry operations. Okay. So let's first, now I have introduced, let's go little deeper to study about these symmetry elements. These are the elements. AOS, the axis of symmetry. The same example I am again taking. H2, H1, H2, C. This is the axis over which you are rotating this molecule. So if you rotate it by 180 degree, you will reach here. Then again, if you rotate it by 180 degree, you will reach here. So total here to here 360 degree, right? From here to here, you are rotating the molecule by 360 degree. Means you are getting the identical structure, or I would say orientation. Okay, and these two are, if you consider, these are, what are these? not identical. These are equivalent. Equivalent orientation. Okay. Same these two are. Equivalent orientation. Okay. So first, you can simply I'm teaching you how to actually calculate or how to know that how many axis, like how many rotations you require to get the identical structure. So basically that will give you the point group of that molecule. See, so from I would say you required two operations, right? You require two operations to reach the identical structure. So how you decide this axis of symmetry, Cn, this, this, we represent axis of symmetry by Cn, let's say. So how you determine this C? I am telling you that only. So C is how many, Cn is how many operation you require to get the identical structure. In this case, for water case, in our example, it is 2. So N is 2 here. So basically, this will be like C2. So the C2 axis is present here in water molecule. This is your C2 axis. 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 So, but this is simple molecule. Let's say if you have a big molecule or any complex molecule which you cannot visualize by just looking at the structure, then how you going to actually calculate this axis or n? How many operations you require to actually get the identical structure? So okay, so there is one formula, n equal to 360 degree divided by theta. This is the important formula you should remember. I mean, you have to have in your fingertips this formula. Then you really, I would say, then you really don't need to see how many operations are required to get the identical structure, uh, how many times you have to rotate it to reach at the, and how much angle is required, how can you calculate the n. So basically, if you know that the angle at which you are rotating your molecule, you will get to know the axis of symmetry. Okay. Plus, one more thing is that this is, I would say, one, you can determine this formula is very important. 2, 3 is that n is also you can calculate by like the number of atoms which are changing their position upon rotation. Okay. If you clearly see this our molecule, water molecule, how many atoms are changing by rotating the molecule? Oxygen is there only. The oxygen is constant, like it is not changing its position. But if you see H1 and H2, these two hydrogen atom are changing its position. So this is another way to actually determine this n. So two H1 H2 are changing their position. So number of atoms which are changing their position upon rotation. So you can also calculate it like that only. But for, I would say, for bigger molecule, complex molecule, it's difficult. It's difficult, and you will ended up getting a wrong answer probably. So it's better you go for this. If you are able to visualize, then it is much better, this one, that how many times you have to rotate to reach the identical structure. That's it. Do operation are were required here. So C2 axis is present here. In that way you can determine the axis. So this is axis. In axis also, in axis of symmetry also, we have like one molecule can have different orientation, like different axes. So on the so how to actually visualize that which one is your principal axis and which one is subsidiary axis. So this principal axis should have axis of highest order. Okay, let's say in a molecule you have C2, C3, C4, C6. Then what will be the principal axis? Your C6 will be your principal axis, and other axes will be like C5, C4, C3, C2. These will be subsidiary axes. So your principal axis will be C6, the highest order of the axis. It will be your principal axis, and other will be, let's say, take the example of BF3. BF3 UVF. Okay, so this is, if you draw the axis, just the axis here, what do you think? This is your, just like you have three, like it is planar, like this only. B is here, boron is here, 1 fluorine, these three are here at 120-degree angle. This angle is 120. Okay, so like this. Now I am not saying this axis is going and passing through the boron, but I am saying it is going like this. It is crossing the fluorine plus the this boron, like this. So it should be C2 axis. If you can imagine, see, if you rotate it, C2 axis is present, because this axis is passing through these two molecules, these two atoms, boron and fluorine, these two. So these two will not going to change its position, but this fluorine 1, fluorine 2, let's say I'm considering this fluorine 3, these will going to change its position. Like this. So as I have already told you that how many atoms are changing? Only 2. So which axis should be? It will be. It will be C2 axis. Or one thing is that formula. Then you can determine the n. This should be n, or this should be n 360. This is theta. This F2 is here. Now it reaches here. So I'm simply saying this. Seeing this, it is 180-degree rotation. So if you put theta equal to 180, you will get 2. So this should be C2 axis. Same, one C2 axis will pass from here only. From here. This. One will pass from here. So you will have also C2, also C2. How many C2? You get 3 C2 axes passing through it. Okay. But still, I have told you this is a planar molecule. This is boron. Planar molecule. Now this time the axis is passing through this boron. One F is here, one F is here, one F is here. Like this. If you rotate it like this, let's say I'm rotating like this. So now this time only one boron is changing. Not changing, sorry. From here. It is passing from here. Now, according to what I have said, how many molecules now, how many atoms will change now? If you just like rotate it like that, how many you are not supposed to rotate the molecule, but you have to visualize this axis. So how many molecule will rotate? 3. Fluorine 1, fluorine 2, fluorine 3. So what should be the n? It should be 3. According to our equation, which axis will be there? It will be there. I believe C3 axis. It is C3 axis. So which one will be the principal axis? Principal and subsidiary axis. For principal, axis of highest order. So this will be the principal axis. And these three C2 axis will be subsidiary axes. Okay. Now let's take another example of PTCl 4 2 minus. PTCl 4 2 minus. Okay. So if you guys remember this Cl, okay, this is the structure. Obviously I have to do this, okay. So if you look closely, like maybe my drawing is not that perfect, but these angles, if you look closely, these are 90-degree angles. Okay, these are 90-degree angles. Again, this is planar molecule. See, I can tell you one thing. If your molecule is planar, meaning that you will have highest order of symmetry if you compare with the non-planar molecule. This is the planar molecule. So again, like this, PT is here, Cl, Cl, Cl and Cl, like this. Now again, this is the axis. So if I rotate to get the identical, let's say not the identical, this time I'm saying let's get the first equivalent structure. So at what angle we should rotate to get the first equivalent structure? That the least minimum angle is required to get the equivalent structure. It should be 90 degree. Let's see how. Let's say I'm just notation. This is the notation only, not anything else. 1 Cl1. This is Cl2. Let's say this 3. This is 4. If you rotate it like this is the axis. If you are rotating planar molecule, I already told you. So you will require angle of 90 to reach the first equivalent structure. Would be Cl, Cl, Cl. So this would be what will be 1. I think I did something. This 3. This is, let's say 4. 1, 2, 3, 4. Yes. 1, 2, 3, 4. See, one operation only. 90 degree operation. 90 degree rotation. At over this axis. Over this axis. Now, if you do these operations for 4 times, let's say 90 degree, again 90 degree operation, rotation, what you will get? This 1, this 2, this 3, this 4, right? Again, this is 1, 2, 3, 4. This is again 1, 2, 3, 4. I believe you guys are following what are these 1, 2, 3, 4. This is just the notation. This is Cl1, Cl2, Cl3, Cl4, PT. This is 2 minus, PT. This Cl. Okay, I believe. So, how many operations you have required to reach the identical structure? This is your identical structure here. This one. 1, 2, 3, 4. 1, 2, 3, 4. How many? 1. Second operation. Third operation. This is the fourth operation. So, how many operations you have required? Total. 4 operations you have required. I have told you that operation will, this operation, how many operations is required? This will give you the n. See, this will give you the n. So this is n. Or, so what will be the axis of symmetry? It will be C4. Okay. Or you can determine by that formula only. Theta 360 divided by what will you, what is that angle here at which you are rotating? It is 90 degree. 4. Okay. So this is the important formula. You, for all the multiple, let's say you are giving exam during the exam you have 50 molecules. For 50 molecules, so you will not going to like draw all the operations and draw these all these after rotating 90 degree. This molecule structure will come, then again structure will come. This you will not going to do. So for exam point of view, what you will do, this is I'm explaining you, that is why I am doing this. This is one structure after 90 degree, this is second structure, third structure, fourth structure, then you will get the fifth structure which is identical to the first one. But for exam point of view, you have to have in your fingertips this one. So just by looking at the molecule, see, this is the PTCl6. I know this is the molecule. This is planar molecule. Okay. Once you, as soon as you realize that this is the planar molecule, okay, 4Cl is there, means this 90 degree is there, means 360, means 360 divided by 90, 4. So your axis of symmetry will be C4. In this PTCl6 you have also other axes also. Let's see, let's look at this. This is the basic class. You might get bored, but I believe if you listen it carefully, you will learn a lot and you will not have trouble finding the point group of any molecule, any complex molecule, believe me. See, I have already told this is planar molecule. Now, I am not rotating along this axis. Now I am rotating along this axis. Let's see this. Here. It is here. Here only. So, this is the axis. This is the axis. If this is the axis, it is containing how many atoms? It is containing 3 atoms. 1, 2, and this 3. And how many atoms are changing here? 1 and 2. So n should be 2. Basically, along this axis, you are rotating the molecule by 180 degree. Again, that your formula is 2. So C2 axis. Now by looking at this, you can determine how many C2 axes are present. Till now, what we have got? We have one C4 axis, one C2 axis. Let's determine how many C2 axes we have. This is one more C2 axis, C2. Okay, we have got one more C2 axis. If you rotate along this axis, let's say 1Cl, 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 PT is here. So now you are rotating like this, 180, just like this. Just flip it. C2 axis. So this is another C2 axis. Again, now if you are not now let's change this axis. This is not the let's change this axis from here to here. This now you will do like this. Or if this is the axis, it will be like this. So you are basically changing your molecule by 180 degree. So this is also your C2 axis. So this is also your C2 axis. This is also your C2 axis. So 1, 2, 1, 2, 3, 4. I believe C2 and C2. I believe you understood that 4 C2 axes are present. So overall C4 and 4 C2 axes are present. I think till now it is okay. You have understood. So as per our definition of principal axis and subsidiary axis, this will be our principal axis for this molecule. These 4 C2s are subsidiary axis. Okay. I believe till now you are able to determine the axis of symmetry and principal axis of that molecule. Okay. Let's take another example, which is not planar molecule. These not planar molecule, these are tricky ones actually. If you not look closely, you will actually end up getting a wrong result. Okay. Example, NS3. So it looks similar to like BF3, the same example I have given, like the BF3, right? This, and this. Okay. This I have told you this molecule is planar, right? This is planar molecule, and this also looks similar to this NS3 and BF3, but this molecule is really planar, or it is non-planar molecule. So before studying this symmetry and group theory, you must have to have this good amount of knowledge about molecules, their structure, periodic table, and their uh, orbital diagram. Then by just giving this NS3 or BF3, you will be able to draw the structure of the molecule. And if you do draw the correct structure of the molecules, then there is a possibility you will determine the correct point group or axis of the molecule. Otherwise, you will end up getting wrong answer. This is fluorine. This is hydrogen. What is this? Boron, I would say. What is this? This is nitrogen. So what are the difference? What is the difference here? This is the difference here. NS this nitrogen 7 14 atomic orbital diagram 1s2 2s2 2s2 2p3. Okay. See why? Maybe you look that this is very simple. You can find it very simple, easy, and boring for you guys. But believe me, this is the basics. If you learn it properly, you will able to find the point groups of any complex molecule. Otherwise, if you miss this basics, it will be very difficult for you for complex molecule to visualize actually, because complex molecule, they will not in the exam, or also you will not able to see by looking at the molecules. This is R, S, it is planar, non-planar, it is cis, or it is trans. So it is very important to learn the basics. So this class is basically for basics. After this, after 1 hour, I am going to start the question answer session. which you guys have already got. I think you have submitted also. So let's see. So 2s2, 2p3. Okay. Now this 3h were here. H is 1h1, 1h1, 1s only, 1s1. This is so 3h are 3h are there. 3h. Let's say I'm just they will bond will give you ns3. But in our valence band of this valence shell of this nitrogen, 2s2 and 2p3 is present. So 2p3 made bond with 1s1 of 3h atoms. 3h atoms. Okay. But these 2s2, these two still remains as it is. So these are the lone pairs. This is the story, different from this BF3. Okay. Now, so this is BF3 is planar molecule, but because of this lone pair, this is not the planar molecule. This NS3 is non-planar molecule. So that is why I am saying it is very important to actually draw the molecule, and know the orbital diagram. How actually what is the correct structure of the molecule? Then you can find this point group and any operation or axis, anything. But without knowing the correct structure of the molecule, it is very difficult to actually find out the correct point group of the molecule. BF3, I am comparing again because I think it is good example to understand things. See, I am not drawing this. This is going up, or let's draw. Okay, maybe this is not good, but suppose this is. It is BF3 is like this in the plane. B is here, F, 1F, 1F, 1F. But this NS3 is not planar because of the lone pair. So let's consider like this. These three. 1H, second H, this is the third H. This is third H. And here you are having nitrogen. And this is the lone pair, let's say here. This is the lone pair here. So that is why, because of the lone pair, it is not planar. It is non-planar, like this. You must have heard about this lone pair, bond pair repulsion in your BSc, MSc, I believe so. So because of that, this lone pair, bond pair repulsion is high. You will not see planar molecule. Because of that, here BF3 was planar. That is why we are able to draw this. We are able to see this this C3 axis from the top of the just the axis passing from the boron. It is rotating the molecule by 120 degrees 3 times. You will reach the identical axis. So the C3 axis you are getting. But in this case, NS3 is not planar. By rotating it from the above by along taking this lone pair and the nitrogen atom here, this one. This is your C3 axis. This axis of rotation is passing through the lone pair plus this nitrogen atom. That is why if you rotate it by 120-degree angle, 120-degree angle, 120-degree angle, you will reach the identical structure. So 3 operations were required to reach the identical structure, or I would say this n 360 divided by 120-degree angle is give you 3. So C3 axis is present here. Okay. But what is the difference between this one and this one? Difference is that if you pass the molecule, if you pass the axis from this by cutting these boron and fluorine, you will get the C2 axis. 120-degree, 180-degree you are flipping. But here in this NS3, there is no C2 axis is present. That is the difference. That is why I have explained you this orbital diagram, this 1s2, 2s2, 2p3. This lone pair is making your life trouble. See, here no C2 axis is present. No C2 axis is present here in this. So you must remember this example is very like good. I know, I don't know you know or no don't know, but this example is very good. So no C2 axis is present. No C2 axis. This is actually during my days, this example was the famous example. My professor used to teach me this, and actually during that time my first exam was there, and he asked this question. This is the first question of that course of the first quiz, and I like I was not mindful enough to actually consider this lone pair, and I have said this also have C2 C3, this also have C2 C3. These two examples have no difference, and I got 0 in that exam, in that question only. That is why I remember it so correctly, that you must have to remember the structure of the molecule. This is the important thing. Okay, so basically in this you have this principal axis. This is principal axis. You have C2, 3 C2 axis, this and this. So 3 C2 axis, these are subsidiary axis. Okay, subsidiary axis. This is principal axis. But here no C2 axis is present in NH3. So this is your principal axis. Okay, this is your principal axis. So no C2 means no subsidiary axis. No subsidiary axis. Okay. One thing, by looking at which example, I would say I have given you one example, PTCL4. Okay, consider that same example. Now I am giving you one trick. Okay, so trick to actually find out that without rotating the molecule, if you determine only the principal axis of the molecule, you will able to see you will able to get the number of operations, how many operations or some similar operations are you can easily determine without rotating the molecule, even without visualizing the molecule. But first you have to determine the principal axis. So let's say PTCL4. Okay, this is PTCL4. Okay, in that example, if you remember correctly, I have said that C4 axis is present because this is planar molecule for 90 degree, 90 degree, 90 degree. This is C4 axis present, and C2 were here, 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 and here. So 4 C2 axis were present. Okay. Now trick. What is trick? Huh? If you determine the principal axis, of the molecule, principal axis of the molecule. Let's say you don't know how to determine this. Okay, let's forget about this. Let's say you are smart enough to get this C4 axis. Now, how to determine how many subsidiary axes you have in the molecule? So, if Cn, this is your principal axis, okay, then you have to have n number of C2 axes, or you don't have any C2 axis. Simple rule. You don't have any C2 axis. So, if you determine principal axis, let's say in this case, I have told you this one, C4. Okay, this is C4. Which means, what it means? It means you have 4 C2 axis, or you have 0 C2 axis. So if you determine only one C2 axis after principal axis, you will simply say, oh no, I don't want to see any other C2 axis. I know if I determine one principal axis, which is C4, and one C2 axis. Let's say you have seen this molecule like this, PTCl4. Okay, now I'm seeing to this. This is the C2 axis. If you flip this molecule, you will get the similar equivalent structure, not the identical one. So you got to know. Okay, I have found out that one C2 axis is present in the molecule, meaning that okay, now I am not going to see any other axis. How many C2 axes are present, from where it is cutting, from where it is going? No, I don't want to see. I want to save my time because I have other questions to solve. Okay, let's say you determine C4 axis and one C2 axis. You will simply say that okay, my molecule have C4 axis, which is principal axis. One C2 axis you determine, meaning that you have 4 C2 axis. These are subsidiary axes. Okay, this is the trick. This is the trick. This is the trick. You can determine it easily because you have to save the time. Why you will see again find this? Okay, one C2 axis is here, another C2 axis is here, another C2 axis is here, another C2 axis. Okay, now I know 4 C2 axis are there. So now I can confidently say 4 C2 axis are there. But if you remember this class, if you remember this trick, you simply determine the 4 C2 axis are present. Okay. So in this course you will learn lot of tricks to solve the questions basically, and I will teach you by explaining the questions only, by giving the examples only, because this symmetry course is not a theoretical course. I would say if you understood the example, it is better to teach by examples, and it is better for you also to learn from examples, because if you teach you like only this trick only, principal axis this, principal axis, if you have Cn axis this, and I am not given you this example, you might not have connected well that how this trick is working. So it is, if you are going for national exam, GR, any like CSR exam, or any GATE exam or any other exam, it will be beneficial for you. You will simply solve the like problems. And I am considering this class as not the very people from PhDs just like me. I'm considering these people are from everywhere. Like maybe PhDs are there, maybe MScs are there, maybe BSc are there. Maybe some people after their 12th standard they are attending this class. Maybe someone is preparing for JEE, IIT JEE. So that is why I am explaining in very layman language, so that everybody can understand. Of course, those who are in PhDs, they will find this classes very boring, but I believe this is very basic, and this will, I think, very helpful for common audience. Okay, now uh, another example I would give you about, let's say, benzene. Okay, maybe my drawing is not that great, but still you can manage. Okay, now comment and tell me that this molecule is planar or not. Anandi goes. You are the first one to join this meeting, so just type this is planar or or it is non-planar. So I can see your chat. Yes, planar. Yes, it is planar. It is planar molecule. This benzene is planar molecule. Okay. How about this? H. This is 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 H. Okay. Now how about this? Is this planar? Now still it is planar or it is non-planar? What do you think? Planar still. Okay. Okay. It is planar actually. Reason, there are plenty of reason for this molecule to be planar. One of the reason, in a very crude way, I could give you is that the number of double bond are like I would say double bonds are present in a cyclic manner. Probably, but this is not the correct way to say things. But still, to explain you well, and because it is uh, it is not true actually for all the cases. Even though molecules are cyclic, double bonded, but still they are not planar. Still not planar, because if you have more number of, okay, we are going ahead of this course. I mean, diverging from this course, but still, see, let's say you have 10 cyclic carbon chain like this, like this. It might not actually, it is not planar, so we will figure out in other courses. Anyway, this is planar molecule. So as I've already told you that if the molecule is planar, it has higher symmetry compared to the non-planar molecule. You have seen one example of that also. See this example, this NS3 and BF3. See, here you got only C3, NS3, only got C3 axis. But for BF3, how you got C3 also and C3 and 3C2 axis also. So which one have the higher symmetry? This one, BF3 has the higher symmetry. So what I have said this, if the molecule is planar, the planar molecule have higher symmetry than the non-planar one. Okay. Okay, coming to this one. What do you think this benzene ring have? I can simply determine this. If you go along this direction, you will have one C2 axis. Or, as I have explained here, according to our trick, this trick. Let's say follow this trick only. We have determined one C2. So this is the planar molecule. I'm just any axis I'm considering, and just flip the molecule 180 degree. C2 axis is present. So what I found? One C2 axis is present, which I found. Okay. Now this is a planar molecule. This angle, if you know this angle, I don't know how many of you know or not, but if you know this angle, if you draw like from here, passing the axis from this point, this is the polynomial, just like this. This is the axis. Okay, and you are rotating this axis, so your molecule is rotating like this, like this. So let's say this is your axis. I would say this axis is C6. Let's say consider this H1, H2, H3, H4, H5, H6. So this H1 will go to H2 and so on. So C6 is present here. So what I know from this molecule? One C6 is present. Simply, nothing else. From my trick, from this trick, which I have highlighted from yellow in the yellow color. This one. Okay. You will simply determine that if this is the case, you have so one C6 axis and six C2 axis. This is your principal axis. Why? I have already told you. This is subsidiary axis. I have already told you. Why this is principal axis? Because it has higher symmetry. Higher order of symmetry, I would say. Okay. Now, let's. I have taught you about element, only the axis, not the plane, not the inversion point. But let's look at the operation. Let's look at the operation of this molecule, the operation of this axis. See, number of operations. Let's say again I am considering our first example, water molecule, simplest example or simplest molecule. We drink this molecule on daily basis. Without this molecule we cannot live. See, how many operations are required? Two operations are required. See, water molecule C2, one C2 axis is here. This is C2 axis. This is the number of operations. This is n number of operations. Second, this is the second operation. You will reach this one identical structure. Okay, these are the equivalent. Anyway, so in case of axis of symmetry, this is the axis of symmetry. Number of operations will be equal to the number of steps to get the identical molecule or structure. So here in this case, this is number of operations is 2. I think I have told you this. Yes, I have told you this. Anyway, so okay, why I again talking about this? Because you don't have to actually actually do the operation and see that how many operations are required to get the identical structure, and you are operating again and again and again and again. No, you don't have to do this. If you determine, I'm again telling you, if you know the correct structure of the molecule, it's make your life easy. It's literally make your life easy. See, if you know the structure of this, this water molecule, why I am not drawn planar again? See, oxygen, you know, 1s2, 2s2, 2p, 4, I guess, and 2 let's not 2 here, hydrogen, 1s1, 6, 18, 1, 1. Okay, so this p is uh, like this, 2s is like this, and 1s, this is 1s here, 1s and 1s, no, two hydrogen molecule, one hydrogen, second hydrogen, hydrogen 1, hydrogen, let's say this is hydrogen 2, so hydrogen 2 is to bond with this. How many lone pair it will have? 1 and 2. The same example I gave you about BF3 and S3. Again, that is why I have not made this molecule planar. Maybe this is trivial, very trivial. I would have made it like this on that only, like this. Why not? Because it has two lone pairs. That is why I am saying you have to have the good amount of knowledge to determine the structure, to get, like, if I give you the molecule and if I give you the molecule, you will be able to determine the structure of that molecule. If you determine the structure of the molecule, I believe you will be able to end up getting the correct structure as well as correct point group of the molecule. So this is wrong actually. This is wrong. Because of these two lone pairs, this the same thing I am repeating again. The lone pair, bond pair, repulsion. The BSc first year. That is why these two lone pair are here. That is why it is not planar. That is why only this C2 axis is present here. Okay. So the trick is here that if you want to determine the number of operations, hello, are you guys able to see my screen and my voice? Am I audible? Am I visible? My screen is, just type yes, no. Anyone? Okay, thank you. Okay, thank you. So, number of operations for this is, we are talking about axis of symmetry. Okay, if you determine the principal axis, so here why I told you about this again, this and this is wrong, this is correct, this is C2 axis. Other than that, we don't have higher order of symmetry, because this is the principal axis of your water molecule. So for any axis of symmetry, let's say if you determine that it is Cn, so to get the identical structure of that molecule, you will require n number of operations. This n is same. This is n is same. So if this is C2, here principal axis is C2 here, means that you will require two operations. to get the identical structure. See, see this one. C2, this H1 goes here, H2 goes here. Again C2 operation. Again H1, H2. See here, from here to here. This is these first one and third one are the identical structure. So to get the identical structure, we require only two operations. So this is the trick. Number of operation is required is this. So again, if you determine the correct structure of the molecule, then you will determine the correct principal axis. If you determine the correct principal axis of the molecule, means number of operations, and you will simply figure it out. And then that again, that trick I have already told you, that you will also be able to determine the number of subsidiary axis if you determine the principal axis, 4C2 axis in that PTCL4 case. Okay. For example, so identical structure means, this identical structure means, what does that mean? Let's say Cn, and you are operating for n times, you will get the identical structure for identical molecule. For example, this you have to remember. This you have to remember. This is the elaborative way. This is the more like this kind of formula. Your formula you should remember this and this one. Okay. So let's consider the example of C3. So you will require three operations to get the identical structure. So 3 you will get E. Let's say if it is C4, then 4 operations. C5, 5 operations. C6, 6 operations. etc. For example, so you determine like this. The number of operations required to get the identical structure is this. These two are this should be same. Okay, now let's come to second element, symmetry element. Plane of symmetry. Okay. So basically any imaginary plane passing through the molecule that actually which bisects the molecules in two identical parts, which are the mirror image of each other, like so, like this. Here, same example. I'm giving you same example because it will be clear to you to understand that from one example you can really teach the group theory and symmetry. From by taking two or three examples, you can teach the full course. That is why plus it is easier for you guys also to understand, because every time I'm explaining different concept, I'm taking different molecule, then you might not connect well. So that is why taking the same example and explaining that, it will be easier and understandable. So plane of symmetry is like that. Like I have told you, this is the planar molecule, right? Planar molecule. So this is the planar molecule, like this. Okay. Or and I have already told you, we have C4 axis. This is the principal axis of symmetry. So let's say plane of symmetry is like, consider this is the plane. Let's say this is the plane only. This is the C4 axis. It is bisecting all the molecules. all the molecules. PT, Cl, 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 all the molecules. In that case, this is your, so I am making like this is your plane kind of. This is your plane. Considering all the all the 5 molecules. So this is your plane of symmetry. In that case, as I have told you the definition of this plane of symmetry, that the plane is bisecting the molecule like a mirror, reflect like the mirror, bisecting the molecule which have the reflection, like uh, two identical. The mirror is cutting the molecule which have two identical parts which are reflecting each other. It is like that only. But in this case, it is not the case, because the plane is not not any molecule is above and below the plane. So that is why there is no reflection. But the plane is containing all the five molecules. Let's say if you have PTCl6, what do you think? Tell me, this is planar or non-planar? How do I draw? This is planar. Tell me. Anyone. Just type planar, non-planar. Just type. Or is this correct? This 2 minus. Okay, nobody is replying, I believe. Okay. So PTCl6, this should not be there. PTCl6, this is PTCl6. It should look like this. This is non-planar. Okay. This is not planar, non-planar. It is like, this is your molecule. PT is here. Platinum. Cl1, 2, 3, 4. And these two Cl are here, and one is below. So if you consider this plane of symmetry, this is the plane, this is your plane, then it is actually bisecting the molecule, and it has reflection. Like this Cl is reflecting here, this Cl is reflecting here. That was the definition I told you, that imaginary plane which is passing through the molecule, bisecting the molecule in the two identical parts. Like this one is here. If we cut down this molecule, two parts which are the mirror image of each other. So actually this plane is containing 5 molecules. One Cl is here, one Cl is here. So these two molecules are the mirror image of the atoms, are the mirror image of each other. So this was the definition of the plane of symmetry. Anyway, so this is non-planar molecule. Okay, let's discuss about this molecule also. What do you think? This molecule, this is the planar molecule. This have the, here again, this is the principal axis, I would say. This is the principal axis containing the Cl, PT and Cl. So if you rotate it like that, get the C4 axis. Okay, C4 axis here containing this is the C4 axis. Okay, again this is C2, because 3 molecules is in this line. This will go here, these 2 molecules will exchange their position in the same plane, but these 2 molecules, one, let's say 2, it will flip like PT. This is 3, this is 4. So C4 will be here, C3 will be here, C2 will be, Cl2 will be here, Cl1 will be here. It will flip like that. Okay, by considering this C2 axis. So according to our trick, if you remember, if we found out that one C4x, this C4 axis is present, we found out one C2 is present. One C2 is present means that we have four C2 axis in this also. This is axis, but plane of symmetry, how many planes you can see? This one plane I have already told you. This plane is bisecting the molecule, making two identical structure which are reflecting each other. So this is one plane. This is one plane. Just similar to this PTCL4. Now one plane is also there, like this plane. This is your molecule. One Cl is here, one Cl is here, and this is your plane. This is my plane. This one. This is bisecting the molecule. So this Cl, and this PT is, this plane is containing this Cl, PT, and Cl, bisecting the molecule. Two Cl will come here. These two Cl will go there, just like this. So we have one here. This plane I would say. I don't know how to draw it here. It is very messy. Anyway, this one, this plane, if you consider like this plane is bisecting. This is another plane. So how many planes we got? I think we got two plane of symmetry. Okay, POS, plane of symmetry. Another any plane you are able to see? I think yes, there are other planes are also present. See, this time I bisected like this. Now bisected from here, from this. So it will contain again PT, this Cl, and these two Cl will come this side. These two Cl will go that side. So, like, I don't know how to draw here, but it should. Anyway, I'm not able to draw it here. Anyway, so one plane is also here. So three planes. We got the three planes here. So for a maybe more planes are present here, but to make you understand the plane of symmetry, I am giving you example, but don't consider only three planes are present here. So maybe later on we will figure out what is the point group of this molecule. If you determine the point group of the molecule, then your job is done. You can simply determine how many, like, I mean, what is the principal axis, how many C2 axes are presented, how many these planes are present, which plane is present, and center of inversion is there or not. You will figure out. I think maybe for center of inversion case we will also discuss these molecules. Anyway, so how many, like, this this plane of symmetry, sorry, plane. Plane of symmetry. Vertical plane, horizontal plane, dihedral plane, and molecular plane. Okay, this is sigma h, sigma v, sorry, vertical sigma v, this is sigma h, this is sigma d, this is sigma v or sigma h. Okay, so this is the plane, and these are the, like, how many types of planes are present. So this vertical plane, this plane is parallel to the principal axis. Okay, now you know how to determine this principal axis. I think you know very well how to determine this principal axis. So principal axis will be parallel to this vertical plane, or I would say vertical plane is parallel to the principal axis, and this horizontal, this one is perpendicular to the this your principal axis. Let's say for PTCl4 case, PTCl4 case, planar molecule, this is your C4 axis, PTCl4, 2 minus this case here, this. So vertical plane will parallel to the principal axis. So principal axis is this. This one is the principal axis. So this will be your vertical plane. This will be your vertical plane. This will be your vertical plane. This is horizontal plane will be perpendicular to the principal axis. So this is your principal axis. This is your perpendicular plane. So this is your sigma h, horizontal. Okay. And dihedral, this is actually special case, I would say. This is vertical plane that bisects the angle between two C2 axes, provided sigma h is absent. Yes, vertical plane that bisects the angle between two C2 axes, provided sigma h is absent. If there is sigma h is present, means that all the sigma d, these dihedral planes, will be considered as sigma v. So in this PTCl4, these are the C2 axes, right? These are the C2 axes. But this is the plane. Let's say this is the plane. This is bisecting. This is planar molecule. This is the sigma v. I have said. But these are the C2 axes. These two means that it is bisecting two C2 axes. These are the two C2 axes. Means that we should have said the sigma d. But in this case, sigma h is present. This is the principal axis. This sigma h is present, which is why both the sigma d will consider, all the sigma d will be considered as sigma v. So this is the special case actually. If sigma h is present, you cannot say that sigma d is present. All the sigma d, if I will write it like that, if sigma h is present, then if sigma H is present, all the sigma D will be considered as the sigma V. So this is important actually to remember. And this one, molecular plane, the plane that passes through the all the atoms of the molecule. This is this one, molecular plane. Sigma. So this would be sigma H or sigma V. So if this is the molecule for PTCl4 2 minor, this is the molecule. Let's say I've told you this is the axis of symmetry. Axis of symmetry, and this is the plane, the sigma H. The sigma H is containing all the molecules PT and all the 4 Cl molecule, means that it is the molecular plane. It is the molecular plane, not this this. I said that this is sigma V, this is sigma V for PTCl4, but these are not the molecular plane. For this case, this is your molecular plane. Sigma H is your molecular plane. Anyway, in that case also, I would again tell you that sigma H have, if any molecule have sigma H, means that molecule have higher symmetry, higher order of symmetry. These are the few things you can remember. If you remember those things, I think it is easier for you to figure out point group later on. When you find out the point group, it is easier to remember, like easier to find out the point group. Let's say if you determine any molecule having sigma H, means that you will simply go for the higher order of symmetry, like you will not go for lower order of symmetry. Then it will be easier for you to determine the point group of the molecule. Anyway, so let's say in that case also, here dihedral plane. One more condition is here for dihedral plane, for these ones, for these, that the vertical planes passing through maximum number of atoms are you guys able to see my screen, and am I audible? Just type yes, no, anything. Vertical plane passing through maximum number of atoms. Okay, thank you. Is called sigma D. This is also one important parameter. Take the vertical plane. I have said this. No, this is PTCl6, PTCl4 2 minus. This is your sigma V. This is your sigma V. I have said that if sigma H was not present, sigma H was not there, then we could have considered sigma. These planes we could have considered sigma as a sigma D, but no, these are not the sigma D. Sigma D should be going like it will contain maximum number of planes like this. See, PTCl4. See, I told you if plane is passing like this. See here, but it will containing only platinum, PT. But if you cross, like if a plane is going like this, cutting the molecule like this, so this Cl will go there only, because plane is containing now three molecules: this Cl, and this platinum, this one, like here. So this is the plane. This is your plane. This is your plane. If it is like that, then you can consider this as sigma d. This only containing, if you have competition between these two, like which one you call sigma d and sigma v, when sigma h is not present. So molecules, the plane which is containing more number of molecules, the atoms, will be called as sigma d. So this will be your sigma v, this will be your sigma d. See this one. Okay. So this is your sigma d. Okay. Now again, point group is this. The element is plane of symmetry. Element is done, but let's see number of operations. Like similar we have seen for axis of symmetry and number of operations for the symmetry. So number of operations for in case of plane of symmetry. Similarly, we have seen number of operations in case of axis of symmetry. Okay, now consider same molecule, same example, our favorite example, water. Okay, now till now we only know that we have only C2 axis because of the lone pairs. Okay, we have only C2 axis present here. Number of operations in case of plane of symmetry, let's consider how many planes are present here. This is the axis. So, do you think any plane is present here? Which is the plane which can bisect the molecule. So, this is your plane actually, which can bisect the molecule. Oxygen is like that. This water molecule is like that. This is your oxygen. Let's say this is your oxygen. Here. This is your. Let's say this is my oxygen. This is H, one H. This is two H, second H. If you bisect it from here, it will reflect. This one go to here. This will go to here, and O will remain as it is. So this is your plane. Sigma. I don't know. This is sigma H, sigma V, or sigma D. So let's find out which one is this. For sigma H, what we have seen? We have seen that for sigma H, that it should be sigma H. It should be perpendicular to the principal axis. So in water molecule, what was our principal axis? Our principal axis was C2. So is it really perpendicular to C2 axis? No, it is not perpendicular to the C2 axis. It is parallel to the C2 axis. This plane is perpendicular to the C2 axis. So this is C2 axis, or this is C2 axis here. Hi, are you able to see my screen? Am I audible? Just type yes or no, because my internet connection is not stable, so that is why. Yes, okay, thank you. So, is it really perpendicular or parallel? So, I can see that it is not perpendicular to the principal axis, because Principal axis is C2 axis here. This is parallel to the C2 axis. So according to the definition, it could be parallel, this sigma V or sigma D, because now sigma H is not present anyway, because this is your principal axis, this C2, this is your principal axis. You don't have sigma H perpendicular to that axis. This is your perpendicular. This is your water molecule. This is C2 axis. This is C2 axis. So this will be your perpendicular plane. This is your perpendicular plane, right? So it will not going to cut your molecule in a bisect your molecule in a identical pieces. No. So sigma H is not present. So what we have figured it out? Sigma H is not present. Actually not present. But sigma. So what are the available options are there? Sigma D or sigma B? Because I have already said that sigma D should we have said that we can say that sigma D is present when sigma H is not present. So now it is good candidate that sigma H is not present. Actually it is not present here anyway. So sigma V or sigma D. So it is perpendicular to this. This is parallel to this C2 axis. This plane is parallel to the. Now one thing I said that it is containing. It is for sigma D. It also bisects the two C2 axis. It's for sigma D. Sigma D also bisects the two C2 axes in our water molecule. This water molecule. Do we have any other C2 axis other than this C2 axis? No. Which means that no sigma D is present. Which means this plane is sigma V. So sigma V is present, C2 axis is present. So this is your plane. This is your. Okay. So by bisecting from the middle, it will contain only oxygen atom. This H1 will go to H2. This here. This will go here. So this is sigma V1. First operation. Again, this plane is operating sigma V. Second, you will get the sigma H1 here, H2 here. This one. So these two are the identical. Now we have also figured it out that identical structure we were getting by operating from axis of symmetry, by rotating by the rotation only along the C2 axis, 180 degree and 180 degree, we reach the identical structure. In this case, we are dissecting the molecule from in between. We have plane, just like the mirror. It is reflecting, not the rotation. Axis of symmetry represents the rotation, but plane of symmetry represents the reflection. A reflection. Here reflection is there. But again, we are again reaching the same conclusion, reaching the same structure, identical structure here. So two sigma B were there. I mean, say two operations are required. So this is your number of operations. So how many? So because we are dealing with this plane of symmetry and how many number of operations is required. So for this example, I think I have summed up all the things from the initial whatever we have learned: sigma, axis of symmetry, reflection or rotation, rotation, sigma, this axis of symmetry, plane of symmetry. Now number of operation is required is 2. Number of operation is required 2 to get the identical structure. I am again saying identical, not the symmetrical, not the this equivalent, identical. Identical means exactly same, not dissimilar, not similar, same. Let's say this is H1. Again, we have reached the H1. This is H2. Number of operations required to reach the identical structure is 2. So one thing also you can remember, similar structure is equal to equivalent structure. Okay. Next thing is that same structure. This is, there is very minute difference, but this difference is huge in the terms of symmetry and group theory. This is the same structure, means identical structure. This thing you keep in your head every time you are dealing with symmetry and group theory. You have to remember this. You cannot forget this. Because if you cannot determine it is similar structure, equivalent structure, or it is same structure, identical structure, then you keep on getting the wrong answer again and again and again. I'm telling you. Because see, if this water molecule, the same water molecule, if I'm not highlighting H1H2, see H1H2, I'm not highlighting. How you will going to figure it out that which one is identical, how many operations you have done to reach here, 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 how many operations are you have done, we have done, how many I mean which one is similar structure or which one is same structure, which one is equivalent structure, which one is identical structure. So you have to remember that similar structure is not identical structure, it is equivalent structure. Same structure means identical structure. That is why then you can reach the uh, the the axis of symmetry. You will end up getting the correct axis of symmetry and also the plane of symmetry. We have learned only two elements today, so that is why I'm telling you about only two elements. Otherwise, I would say simply not H1 H2, simply you from here to here. See, you have rotated by 360 degree or 180 degree or 90 degree or I would say 45 degree. So it doesn't make any sense actually. So you have to remember that it is, so you have to remember that it is actually rotating or reflecting, but rotating or reflecting, but it should give you this equivalent this sorry this identical structure. Then you can correctly determine that, see, H1 H2, if you rotating by 80 degree, 180 degree, 2 1, again 180 degree, 1 2, okay, then you can say that okay, from here to here it is identical structure. Now if you uh, Anandi sir, there of us have a class from 6 p.m. So we are leaving now. Thank you for the class. Okay, Anandi, you can leave, but join next. Join for the next class, which is going to happen at the on the Sunday at the same time, 4 p.m. Okay. Now you can leave, but you can join later on. Like the and give me also feedback how you are liking the class. Is it too boring, too slow, too fast? Is it valuable to you or not? Just type it, so after that we can end this class and I will be more prepared. And you guys have any doubt, or if you guys want any specific portion to teach, assignment to solve, anything, I thought I will be able to solve the assignment today, but today I will be not be able to solve. But in the next section, I think uh, in the next meeting we will be able to solve the question and answer. So just comment here and tell me how do you want, like, okay. mm, Someone is saying class was very helpful today, sir. Thank you, sir. Okay, join Saturday. Oh, sorry, Sunday, same time, 4 p.m. next Sunday, coming Sunday. Anything specific you guys want? Tell me, just tell me. Have you guys solved the assignment 0, assignment 1 problem? I think you got assignment 2 also. Are you guys able to solve? Have you solved, or anyway, I will be able to, I think I will solve this question. Yes, sir, solve assignment 1. Okay, anyway, in next class I will teach for 1 hour, and for 1 hour I will solve the question answer. Assignment 0, assignment 1, assignment 2. If assignment 3 will be there till then I will be able, then I will solve assignment 3 also, and I will progress it like that only. Okay, so okay, now I am ending the meeting here, and thank you everyone. Join again Sunday, same time. Okay, bye, see you then.